All right, I want to make a quick video that explains a little bit of how to use the Hardy-Weinberg formula. So let me share my screen, and then I'll open up the document and work through some of these examples with you. So as you can read here, the Hardy-Weinberg equation describes the relationship between allele frequencies. So for example, dominant versus recessive, like what percent of the gene pool has the dominant allele and what percent has the recessive allele, right? That's one description. And also genotype frequencies in a stable population. So again, with the genotype frequencies, for example, are we talking homozygous dominant, homozygous recessive, or heterozygous, right? What percentage of the population is homozygous dominant? What percentage of the population is heterozygous? What percentage of the population is homozygous recessive, for example? So here we go. And this is the basic formula. When we're talking about allele frequencies, again, when we're just trying to figure out dominant versus recessive, it's a very simple formula. It's simply P plus Q equals 1, meaning obviously the frequency or percentage, if you will, we don't use percentage signs in the situation, but you could think of it as a percentage. The percentage of dominant allele versus the percentage of recessive allele, right? The frequencies. And again, these two numbers will always add up to 1, which makes sense, right? So imagine if it was 50-50, it'd be 0.5 plus 0.5 equals 1. That's the allele frequency formula. The genotype frequencies, right? This formula is P squared plus 2PQ plus Q squared equals 1. And that one is a little bit more complicated, but it still always equals 1. So again, if we're dealing with genotypes, right? So you can imagine, P squared represents homozygous dominant, 2PQ represents heterozygous, and Q squared represents homozygous recessive. So again, it always has to add up to 1. So for example, if P squared, so homozygous dominant, let's say 25% was homozygous dominant, right? And then let's assume 50% is heterozygous, right? So that's 25 plus 50 is 75, right? So therefore, obviously, the only thing left would be 25% would be homozygous recessive, because again, it all adds up to 1. So here, let's look at some specific problems, right? The steps you need to take to determine these things. The first thing you'll need to do is identify the known value. So most problems start with either the frequency of the recessive phenotype, or Q squared, right? Or the frequency of the alleles. So again, we're either dealing with alleles, right? So P's or Q's, or we're dealing with genotypes or phenotypes, right? So Q squared, which is homozygous recessive, right? Or Q squared, excuse me, P squared, which is homozygous dominant, or 2PQ, which is heterozygous, right? So to find the allele frequency, if you know the Q squared, right? So if you know the numbers, if you know the percentage, the frequency of the recessive population, then you can just do some simple math, right? You could just take the square root to find Q, right? So if Q equals the square root of Q squared, and I'm going to give you some examples below. So if that doesn't make sense to you yet, don't worry about it. All right, so that's one thing. And once you know Q, then you can find the other allele frequency, right? Because again, P plus Q equals 1. And I didn't show you the math here, but if you did some very simple rearranging algebraically, then that would mean P equals 1 minus Q, right? So this right here, P equals 1 minus Q, it's the same formula as this. It's just rearranged algebraically, right? Same thing, rearranged. And then once you know that, you can calculate all the genotypes. And to do that, you use the P that you figured out, use the Q that you figured out. And again, hopefully this will make more sense. Well, I give you some examples here. All right. So let's look at the scenario. In a population of moths, 9% of the individuals have the homozygous recessive white spot trait, right? So this is just a hypothetical situation. So we know for Q squared, we know Q squared equals 0.9, right? Or excuse me, 0.09, because that's another way of writing 9%, right? So here's what we're going to do. Excuse me, let me back up a step. So the question is asking, what is the frequency of the dominant allele, right? So we know how many of the individuals are homozygous recessive. And using that information, we want to find out what percentage, right? What's the frequency of the dominant allele? So here's what we do. Obviously, again, we need to start off figuring out what Q is. So first, again, we're going to find the frequency of the recessive genotype Q squared, right? We already know that 9% of the population has this recessive genotype. So then we just do some simple math. So, right, so that means Q squared equals 9%. Another way of writing 9% is 0.09, right? So we know that Q squared equals 0.09. So what we can do then to figure out what Q is, again, this is just algebraically, right? You just, what you do to one side, you do to the other. So we're going to take the square root, right? We'll take the square root of Q squared, or take the square root of 0.09. Obviously, the square root of Q squared is Q, and the square root of 0.09 is simply 0.3. All right, so now we know what Q is, right? We have algebraically figured out what Q is based on the fact that we know that 9% of the population was homozygous recessive. So we have Q. So now all we need to do is figure out P. So again, we just plug it into the formula, what we figured out earlier, right? P equals 1 minus Q. So that means P equals 1 minus 0.3, right? Because we've already determined that's what Q is, right? So then what is 1 minus 0.3? That is 0.7, right? So now we know the frequency of dominant allele P is 0.7, right? Simple algebra, right? We knew what Q square was, so we took the square root to figure out what Q is, and we plugged it into that simple formula to figure out what P is. That's one example. Let's look at this example. So now instead of calculating the frequency of an allele, we're going to calculate the frequency of a genotype, whether it be P squared, which is homozygous dominant, or 2PQ, which is heterozygous, or Q squared, which is homozygous recessive, right? So here's the scenario. In a forest, the frequency of the dominant allele for tall trees is 0.8. What is the expected frequency of the heterozygous genotype? All right. So again, the frequency of the dominant allele, which is P, right, we know is 0.8. So based on that, we can do some math and figure out what 2PQ is, right? So step one, find the frequency of the recessive allele, right? So we know P, so let's very simply figure out what Q is. And honestly, just looking at it, whoops, look, it's missing. It's 0.2. Like, hopefully for some of you, that math is easy. Like, what plus 0.8 equals 1? And the answer is 0.2. But let's look at the math really quickly. So again, looking at this formula, P plus Q equals 1, right? We rearrange that algebraically to say Q equals 1 minus P, right? Again, this formula is the same as this. It's just algebraically rearranged, right? So this is the formula we're working with because we want to figure out what Q is. And we already know what P is, so we just plug it in there, right? Q equals 1 minus P. In other words, Q equals 1 minus 0.8. In other words, Q equals 0.2, right? Because 1 minus 0.8 equals 0.2. So there we go. Now we know P, right? We were given P, 0.8. We figured out Q, which is 0.2. So now again, we just plug in those numbers, right? So we know the question's asking about how many are heterozygous, and we know heterozygotes are 2PQ. So we simply plug those numbers in, right? 2PQ. I need to fix this so it'll make more sense when you guys see it. It's 2 times 0.8 times 0.2, right? And if you would do the math on that, then you would see, 2 times 0.8 times 0.2 is 0.16. And then finally, 2 times 0.16 is 0.32. So there we go. We figured out the frequency of the heterozygous genotype. It is 0.32. And another way of saying that is 32%. So that's it. I hope that wasn't too fast. Let me know if you have any questions. And I will point out that for the exam, at least at the time that I'm making this video, any questions you get that deal with the Hardy-Weinberg or that you're required to use the Hardy-Weinberg equation on the exam, I don't plan on having any of these genotype frequencies, right? I don't plan on doing anything like that. I plan on only having basic questions where you don't need to take the square root of anything. And generally speaking, you're probably going to be solving for a allele frequency. But that's it. Again, let me know if you have any questions.